Hello and welcome to today's webcast brought to you by Lightwave Magazine. Today's event, Isolating, Testing, and Troubleshooting FTTx Drops in the Last Mile, is going to be presented by myself, Larry Johnson, Director and Founder of the Light Brigade. But before we start, we want to cover a few housekeeping items. At the bottom of your audience console are multiple application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We will try to answer these questions during the live Q&A portion at the end of this webcast. However, if there's too many, we don't have enough time, I will personally get back to each person who puts a question in. If additional resources have also been provided for this webcast, such as the PDF of the slide deck, and you will be receiving an email from Rick Atchison on our staff and that, so that you can access those. It will be provided to Lightwave Magazine and be downloaded via the resource list widget. You can expand the slide area by clicking on the maximize icon on the top right of the slide area or by dragging the bottom right corner to enlarge. In fact, you can expand and reposition many of the components to your screen. So feel free to do as you desire to give you the optimal webcast viewing experience. If you have any technical difficulty during the webcast, please click on the Help widget as a question mark icon and addresses common technical issues. If you still need assistance, just type your issue into the Q&A widget and a member of the webcast support team will work with you to correct the problem. And for your convenience, this presentation will be available on demand within 24 hours of this live event. And we will be sending an email message as a reminder. And so with that, let's go ahead and start. The first, I'm going to move up, since I already introduced myself, is Larry Johnson, the founder. We went through the housekeeping items. So the fiber optic training history, I think many of you already know the Light Brigade. We're a fiber optic training company, established in 1986. We've trained over 50,000 people. And our goal is to, basically teach what you need to know to make decisions. And whether you're in the design, the installation, or installation repair groups, we hope to provide unbiased knowledge to you, and we always welcome people to join us in our courses. We teach worldwide. The objective, slide 5, this session is to review common problems in FTTx installations and how they are located using various types of fiber optic test equipment. And the focus is basically going to be PON networks because they're the more complex versus the point-to-point active Ethernet or other fiber optic networks. So with our next slide, the introduction slide, I just want to just basically talk about the beginning part, and then we'll expand further in on each of the slides as we go. So we are going to talk about the different types of test equipment, the testing role, the troubleshooting role, maintenance, restoration. We're not going to be able to spend that much time on restorations and cuts, but we're going to focus more on the troubleshooting side. And then, of course, these are going to deal with point-to-point networks, such as active Ethernet, or segments in a PON network, or in the case of a home run topology on a PON, where the splitter is housed within the service provider's facility. We could isolate it as a point-to-point, even though because we're testing after the splitter. And then point-to-multipoint systems, which are PONs in particular. So with our next slide, we're going to talk about the importance of documentation. We really need to know power levels, attenuation levels, reflection levels, because we're going to be doing comparisons to these values and that. So it's to verify that the installation went in correctly, but also to establish maintenance records for restoration requirements. Okay, next slide. And by the way, we have about 40 slides, so my pace I'm going to have to manage because I do want the Q&A side at the end. So on the physical plant equipment, we're going to focus on 5 different areas. The attenuation or signal loss. And in this case, most of this type of equipment people have. We're just going to focus on how to use it and where and when. The OTDR, the optical power meter, the optical loss test set, which is a stabilized light source and a calibrated power meter into one unit. For reflection measurements, we're going to be using the OTDR again. Power measurements, the essential piece of test equipment, the optical power meter. And we're really concerned about the surface quality of connectors, and we'll talk about all these items individually, so the inspection scope. And then as we get closer to drops, then the continuity tester or visual laser. So on the next slide, we want to focus on the fact that connections are very critical. This is how we access the fibers to test them. And that means that cleanliness is going to be very important here. But we have transmitters and receivers, and then a PON network, the optical line terminal at the service provider hub, and the optical network terminal at the subscriber's facility is where our active components are. They're the only ones that require electrical power. Active Ethernet, on the other case, is we have a powered cabinet in the outside plant. And so we actually have two point-to-point networks, one from the hub site to that cabinet and another one from that cabinet to the subscriber itself. And the predominant use of the small form factor SFP modules in use. And then the outside plant, some of the acronyms that we're using, the fiber distribution hub for housing splitters, whether it's centralized or distributed architecture. Fiber access terminals, also known as pedestals, more commonly known. Multi-port service terminals for those that are having pre-terminated hardened connector drops, the MSCs. And then transition boxes, also known as NIUs, that are located on the side of the subscriber's location. On the next slide, we really need to understand and know the outside plant. In this case, you see a picture of somebody doing an acceptance test on a cable reel. But during the initial testing, we want to make sure that, of course, the span's continuous. We want end-to-end attenuation with both optical loss test equipment and also OTDR signatures of the span, making sure it was installed properly. We want the location, the attenuation, and in the case of mechanical splices, if you use them, the reflectance of any splices. We also want to perform optical return loss measurements, which is the entire span's reflection versus the reflectance as an individual component in it. And on the next slide, we'll want to break it down to say, find the common element. In other words, if we have an outage or we have a problem, where's the common point to it? Because that's where our troubleshooting is going to take place. So in this case, we show a PON network with say a GPON with 32 subscribers on one OLT card port. And if all 32 of those ONTs are in alarm, then our management system will identify that, and we have a common element. So the case is it going to be the fiber between the service provider to the splitter, or is it the splitter itself? Obviously, it's pretty rare for a single fiber to fail, so if you have more, fibers to different PONs, you have a lot of alarms going off, then we probably have a more severe outside plant restoration requirement to take place. The odds that it's one fiber only affecting 32 is actually pretty slim unless it is that common splitter, if it is a 1x32 splitter in the FDH or pedestal. In the other cases, as the split counts go down, we can see that one will be doing truck rolls because now we're going to the outside plant. But the other one is we only have one ONT into alarm. Then our problem is going to be more localized, and we're going to be looking at the ONT in particular and the drop cable from that ONT working back toward the splitter itself. Okay, next slide. The importance of testing OLTs and ONTs is critical because we want to use these as baseline measurements for comparison. So the optical power meter is essential here. And so what we want to know is what's the output power of the OLT for downstream power measurements. And then again, we want to also measure an upstream power measurement. And of course, if you have 32 different transmitters transmitting upstream in sequence, we're going to pick up only the peak power. So you're going to see your power meter fluctuating because each of those lasers puts out different power levels. But anyway, it's the peak power that we're looking for. But we're going to be working predominantly in the downstream direction versus the upstream. But we'll talk more in detail. And because of the difficulty in measuring upstream power levels. The optical loss test set must operate in line. So in other words, we have an input connection and output connection with a fiber tap splitter inside the OPM, and we'll talk about it later on. Okay, next page. The importance of understanding that photodetectors or photodiodes have minimum and maximum received power levels. And the graphic that you see on this shows that a certain level in dBm, if we have too much light, we overdrive the photodiode and we'll have a lower signal quality. And on the other cases, if we have too little light, the same effect takes place. So, this is why it's important to be measuring and documenting the power levels, whether it's at an OLT or an ONT, is to know what those power levels are for comparison reasons, but also to compare to the manufacturer specifications to make sure that you're within that safe operating range for the highest efficiency of the system. Okay, next slide. Now, if we're at the subscriber at the ONT, we want to measure the downstream power level, and this is an easy one. And most power meters have different calibration points, 1310, 1490, 1550, 1625 or so. The basic band, which is digital content, is 1490 nanometers, and 1550 nanometers is used for RF overlay using an external WDM at the service provider's hub. So in this case, though, we want to set the power meter at the correct wavelength. We want to measure in dBm and document the power level, check it to manufacturer specifications, make sure that we're operating okay. And we can only measure downstream in this case, but if we already know the OLT's transmit power, and now we know the ONT's receive power, the difference in those two measurements is in dB. So dBm minus dBm equals dB. So we already know what our loss value is now for any of the ONTs by knowing the original OLT measurement. Let's go to the next slide. So the most difficult measurement is that upstream power level from the ONT. And the reason is ONTs have a function called automatic power shutdown, APS. And even though these are class 1 lasers, which are retina safe, it's a safety mechanism built in just because it's just a society where people sue a lot and all this. So we're just being careful in that and putting an APS function in on ONTs. So if we disconnect the connector, the laser shuts down. So what we have to do is we have to use an inline power meter, which is what the animation is showing. And where when we disconnect and we then connect into the input side of the power meter, we need an additional jumper to now connect from the power meter to the ONT. This will allow us to measure both the downstream power levels, but also the upstream power level, because the laser's not catching the Fresnel reflection front end to know to shut down. And that's very unique, and this is something that if you want to verify your upstream power levels, you're going to need this specialized power meter. On the next slide, PON power meters testing ONT transmit and receive. You'll see an example of one of these with a path. So you can see the two jumpers at the top. One of them is your inbound pigtail, and the other one that would normally go into the ONT, and the other one is actually now being a bridge to the ONT so that we can operate in line. And while there is a slight attenuation in these tap splitters, that value is calibrated into the OPM, so you are actually getting the accurate power measurement using this. Okay. And you can get these power meters with different versions based on the wavelengths you're using and the protocols you're using. And they can also perform optical return loss functions, and of course, storing records is critical. Speaking of which, if we go to the next slide, you can see this is real simple just so that we can fit this on screen so you can see it. But at the ONT that we're measuring downstream power levels in dBm, that would be 1490 nanometers and 1550 nanometers, but we're also recording the upstream power level at 1310 nanometers. And then, of course, if we already knew our OLT values from down below, so in other words, our upstream and downstream power levels, that we can subtract those levels from the OLT to the ONT, and that'll tell us our attenuation in dB. And so do look at, when you're looking at power meters, do look at whether you're going to need to do hard copy or how much waveform storage and whether they're designed to handle, especially PONs. And, GPON can go up to a 1:64 split ratio, so it doesn't, how easy is it to work and how functional is it for your application. Let's go to the next slide, focusing on the outside plant. Again, I mentioned this, that once you have a problem with an ONT, then the physical layer OA and M function of the OLT at the OLT will basically determine that we're not getting a signal from an ONT, and it's specifically which one it is. It can't tell us if it's been unplugged. It can't tell us if we've lost power. It can't tell us if it's a cut in the yard or a splitter failure. It just says which one or multiples are offline. But once we know that which ones are offline, then we start looking for the common element. So the example we gave, if all 32 are offline, then it's easy. Then we pull the OTDR, we disconnect from the patch panel so we have access to the panel, and we look at the fiber itself, and we can do an overlay using the OTDR's overlay functions. We can compare those and at different wavelengths to see is there extreme macro bin, for example, that may be the problem. So we want to compare to the original charts whenever possible. So if the power level's too low, then of course it's the problem is going to be prior to that point. But at any point where you're connecting and testing, now switching over to the power meter, and that we're looking for the change and whether it increased or decreased or is the same. And the problem that we're going to get is we go to more subscribers with the drop cable, especially underground in someone's yard, is the shallow placement. And I've seen quite a few installations where people are not protecting the underground cable. Personally, I suggest putting it in Schedule 40 PVC at 18 inches so that the average person digging up, putting a rose bush in or tree is not going to cut that cable. But it's a slight cost, but it's a lot cheaper than doing a truck roll. Let's go to the next chart. Point-to-point, not-to-exceed charts. I'm a big fan of not-to-exceed values. These are spreadsheets that anybody can make, and you base it on different distances or the exact distance that your network that you're installing. And we put down the attenuation values based on the different PON standards, 0.4 dB per kilometer at 1310 nanometers and 0.25 dB per kilometer at 1550 nanometers. And so by seeing the different spreadsheet by distance, we know how much fiber loss, plus if we know how many splices times what value and how many connections are there, then we end up with a total number. And then, so for example, if we took a 20-kilometer active Ethernet span, our total attenuation should be 9 dB over that span. And so if we come in better than 9 dB, great. If our power level started out, say, at minus 5 dBm, and we had 9 dB of physical plant loss, then our receive power should be minus 14 dBm. And again, these are comparison measurements, but we know the physical plant losses. The difference here is these are to help people during the initial installation. It's the actual records we'd like to be using. Let's go to the next slide. PON loss budgets. So some basics on PONs. It's a 20-kilometer distance limitation in the standards. The attenuation values are specified in the standards and noted at 0.3 and 0.4 dB per kilometer at 1490 or 1310 nanometers. We have the theoretical loss value of 15 dB for the splitter, but the actual average with tolerances is 15.8 dB. And connections are a half dB each. And splices, we're using the Telcordia GR20 value of 0.1 dB per splice because the splice standard that is in the FTTx standards is 0.3 dB per splice. And with new equipment, there's no reason you shouldn't maintain the higher and quality splice level and the better performance. But that's up to each individual whether you want to be with the tighter 0.1 dB loss or the 0.3. Let's go to the next one, and we'll look at a not-to-exceed value on splitters, which is going to be very important when we start isolating problems, and that as we continue. And So if the problems could be at a splitter, all it takes is one person with a power meter to isolate the problem here. So first one is measure the, and of course if you're disconnecting a splitter, that means that if you're taking the input side of the splitter, that means you're dropping everybody on the output. So you don't want to disconnect an input if it's only one failure. So if, let's say we had a 1x4 splitter though, and all 4 are offline. Well, in this case, I want to go ahead and disconnect the input port to the splitter and plug it into my optical power meter. I'll be testing at 1490 or 1550 nanometers downstream. And so I want that initial power level. And I want to compare it with what the initial record was when it was installed. And if anything, put little stickers on these ports and just put the power level at what wavelength, easy to look at and can do comparisons. Then take once you know that record, claim the connector, plug it back in, go to the other side of the splitter, and now measure the output powers of the 4 legs. And that you'll see that there's some differences between them because splitters aren't absolutely perfect. But you can now see the difference between your input and your output. A 1x4 splitter, we should average about 6.6 dB of attenuation through each of those ports. So if it's 6.2 to 7, you're still in the range, and that connector repeatability and just tolerances on the splitters. But it shouldn't be that high. However, now if you ended up where you're seeing 20 dB of attenuation at the splitter, it's obvious the problem's in the splitter itself. So we're going to replace the splitter. But the only way that we can really do this simply is we have to have the power meter, and we have to have known records on input and output power levels to be able to do so. And this technique applies to any of the splitters. The number that you're seeing on screen, the average number, is in the G.671 fiber optic passive devices standard, and this is referenced in the system standards that all the values referenced come from this ITU standard. Let's go to the next slide now. So a point to multi-point not to exceed chart. The only difference with this one and the prior one was we've added in the splitter element into it. So we can start saying if we went to the maximum 20 kilometers, we have 8 dB of fiber attenuation at 1310. We have 1 dB because we have 10 splices at 0.1 dB. We have 7 connections in this case, and between the service provider's hub, a fiber distribution hub, input connectors, output connectors, potentially hardened connectors in the outside plant, plus the interface connector at the transition box. And so you can end up with a fair amount of attenuation in connectors and that. So, and then of course the greatest single event is the optical splitter itself. So in this case we would have about 28.3 dB. So that would be our not to exceed in our comparison measurement, but hopefully we'll be coming in much less than that. At the same time, at 1550 nanometers, we're at 26.3 dB. Now, if I was doing troubleshooting and that bottom number was higher than my upper number, see, anytime your attenuation's higher at the longer wavelengths, it means you have macro or micro bends in the system. So I'm always testing dual wavelengths so that I can identify if these are occurring. And if it is, then it's a case of isolating where it is using the OTDR. Of course, it depends a lot on the severity. Again, we don't want to, if there's only one problem, one ONT, I don't want to take an OTDR and be using it, unplugging my fiber, and then causing 31 subscribers to go offline. However, if you're not using the 1550 nanometer wavelength, you can buy a modular WDM with so it would add in about 1 dB into your plant loss. But what you could do is use you'd still be using your 1490 downstream, your 1310 upstream bidirectionally, but your 1550 would not be in use. You could put the OTDR connected to the 1550 port. You would be operating out of band as long as you're not using 1550. You'd be operating out of band, and it's a more sensitive wavelength, and you could troubleshoot an active system. So you'd be using an external WDM for doing so. So let's go to the next slide, and let's talk about the OTDR. So when is it used? Predominantly during the initial installation to make sure everything was installed correctly. The only other time is really when you have everybody offline on that fiber that's linking to the OLT's card. And then where is it used? We're looking for connection points, and predominantly we'd like to test from the central office. We have the dynamic range in the instrument. But when we start isolating problems, we may move it to the outside plant. But we're always making sure that we don't want to interfere with any live customers, any operation. The closer we get to the end, the more skill by the technician is required, but also the less effective the OTDR will be due to the OTDR's pulse width and dead zone limitation. Okay, so next slide, finding the fault. The OTDR is critical to locating where the problem is and the extent of the damage. It doesn't mean a fiber is broken. Like as I mentioned before, it could be an extreme macro bend. So if the cable is damaged more than one PON, we can be affected. So if you have a 144 fiber cable and a backhoe digs it up, you're going to be more than 32 subscribers out. You're going to have a massive outage. So it's, again, you've got to identify which fibers are broken, which fibers are stressed. Don't assume that they all are, so we want to make sure if there are any usable fibers where we could roll to other fibers, we'd have to do a truck roll to it to get to the right fiber, maybe do a mid-entry to access, but or the restoration. But restoration's another webinar entirely. So when the fault's localized around splitters, splices, and connection points, that's where, it's normally, something around that element caused the problem, and that's what we want to isolate it into it. And we don't want to damage adjacent fibers. As we get closer into a location, we're going to be using visible lasers quite a bit, and the optical power meter, again, as the essential piece in that. So key issues on the next slide. Key issues for the OTDRs is making sure that you have the right dynamic range for your instrument. And so normally you'll see on OTDRs you'll get a variety of different options on the different modules that you buy. And when you get the ones that are 30, 35 dB, they're really designed for point-to-point networks, you'd be talking 60, 70 kilometers isn't really an issue there. But the problem is that the attenuation through a splitter, it's just so high. And so we need the larger dynamic range, over 40, 40 to 50 dB, and that for PON networks. And so we want to have the dynamic range. We also want to have a lot of data points and where we sample the fiber. So if you're sampling the fiber every meter, that means you have to have 20,000 data points, and then we're going to increase the averaging as well in that port. We're also going to use the OTDR though for measuring the reflectance of components and then the span optical return loss measurements. Next slide. Let's focus on finding the fault. So use the 1550 nanometer wavelength because it's more sensitive to macro and micro bends, and so we want to see if you have a fiber that failed. It doesn't mean that it failed just at that point. The cable could be damaged further up and down from that fault point. So we want to find out how extensive the problem is, not just where the break or where the specific point is, because it could be more, and therefore the longer wavelength. Also, to make sure that we have a Fresnel reflection so we get good accuracy. A Fresnel reflection is that spike that you see on the OTDRs. And so in real time, I can go port to port to find one fiber that gives me the best reflection. I'm going to use it as my reference point versus a roll-off one instead. And then we're going to use two-point measurements to determine the extent of the damage. So one of them will be at the Fresnel reflection. The other cursor or marker will be moved to where the stress starts, and we'll do it both before and after the break point or stress point. Of course, if it's after, then we have to do a truck roll to take the OTDR to the other end. And expand by using your resolution on your vertical and horizontal to get the best location. And then for the most accuracy, measure from the previous splice point versus from the central office. Okay, so next slide. So we're showing here a graphic of different types of products where they can be used and so forth. But I added in some different elements that are, what your pulse should be and your averaging and so forth. So the closer in we are, we usually will test with a shorter medium pulse, and we don't have to have that extensive of averaging and that with the instrument. But as we go farther away and toward the subscriber, while we're still maintaining, say medium distance, we maybe with a medium pulse bit, but once we get to that drop cable and we're going through a splitter, you're going to have to go to the shortest pulse width with the greatest amount of averaging taking place to be able to even get a trace into a drop. And we'll talk about some of the challenges on the drops a few more slides up. Next slide. So, and by the way, if you haven't picked up on this, I'm in a remote location versus the person that's actually managing the slide presentation, so I'm having to clue them. So my apology for this irregularity, but sometimes you just can't be where you'd like to be in that. Reflective OTDR signatures. In this case, we've zoomed in on a Fresnel reflection, and this is what I was talking about. You can see the B markers placed right at the knee of that reflection. And by zooming in using the vertical and horizontal, I can get a real accurate placement. I can let the instrument do it as well in auto functions. I'm just one of these old timers that likes to do things manually. But reflective OTDR signatures, connectors, the end of the plug itself, the ferrule. Open fibers, it's a good patch panel, and that could be a broken fiber that has enough of an angle on it that we can still get some light back. But we are going to use these as reference points. Let's go to the next slide where we'll show the difference between a non-reflective and that, which when I see a non-reflective signature, and that for the most part, I don't like them because they're trouble points, and that, unless it's a fusion splice, but then we're not seeing a large drop-off, which is what we're seeing here. And that, so remember on the previous one where the B marker was, and now look at where the B marker is versus where the fiber end appears to be. And that, so one thing is normally from a roll-off, it's one pulse width back is where it is. But rather than guess on where to put that B marker, I really want to have a Fresnel reflection, place it accurately, and then all the fibers should be at that same point. But events that cause non-reflective signatures, extreme macro and micro bends, breaks, water so if it's an underground placement and the cable's broken or so, and then water has a closer index of refraction to glass than air does. For those that have older cables where you have gel in the cable, it also has a closer index of refraction. And then of course fusion splicers, macro and micro bends. So let's move on and look at a splitter signature. In this case, we're seeing a OTDR trace with a 1x4 splitter. You can see where the splitter is, where we have a non-reflective, so it's a drop-off there, event number 1. And in this case, so we see non-reflective, so it's not a connection, it's just a fused biconical taper or planar splice. And then we see the Fresnel reflections at the end of the drop cables for 4 different users. We're fortunate in this case because the lengths are different, and that if they were the same length, they would just lay over each other and we wouldn't be able to see them, and that's why the OTDR is now limited in some of its ability, and depending on the length and the separation of the physical drops, as well as the OTDR's dynamic range and the pulse width as well. And let's go to the next slide about testing drop cables. And one thing, when it gets harder when we get closer to the subscriber because the OTDR gets limited because of its pulse width and that on what we can do. And so, and secondly is if we're only talking about a few users that are having problems, then the OTDR from the hub, we're not going to be able to use it. We'd have to take it into the outside plant and then hook it up to the drop cable. And in this case, the easiest function is going to be using the optical power meter instead. And so in this case, we would take the power reading at the ONT and document it. Take a look, compare it to the previous. Is it the same? If it's the same, then the problem's not in the fiber before it. Okay, if the loss is increased, then we go back to the prior connection point. Maybe it's a pedestal or an MST or an FDH, and then we test the output power of that connection to that drop cable. The difference in the power levels is the attenuation and the drop cable itself. And in that case, is it an aerial drop or is it an underground drop? If it's an underground drop, if we're not getting light, then we've got a failure. I'd look for, who planted the newest tree. On an aerial drop cable, then we're looking for saying, okay, did we have a break in a connection? Is there a shotgun pellet in a cable or so? Did a squirrel eat through the cable? Those type of things. And then again, we can also use the red laser, which has a dynamic range of about 1 to 2 kilometers anyway. So we can do a quick continuity test, but the power meter is going to be the essential piece. Let's go ahead to the next slide, troubleshooting PONs and active Ethernet systems. So testing drop cables, they're short. We want to keep it simple, so we're going to use the power meter, as I said. So we're going to test the downstream power level at the ONT, and we're going to compare it. Then we're going to move up to the next point, and we're going to do a test, a measurement there. If the power level is still lower at the test point upstream, then we go one more connection point up. So we're working toward the service provider from the subscriber for this. Another element too is if you take a look at the length of a drop cable, the number of splices, the connections there, the attenuation is so minimal. It's normally 99% less than 1 dB for a drop cable. So again, we're looking, we shouldn't be seeing extreme losses at this case. And again, when we're talking about connectors, cleanliness is going to be very critical. People think that dust caps are clean. Dust caps are rarely clean from the time they're manufactured to the time that they're actually put on the connection. They're injection molded in a factory environment. They're shipped in bags by the pounds or kilos to the manufacturers and so forth. So assume that the dust caps are dirty. Assume that the connector's dirty. Clean it, prevent damage from occurring, and reduce reflections. And a lot of times with hardened connectors, I'll see where they have the dust caps that thread to each other. So when the hardened connector's mated, so are the dust caps. But many times I'm driving down a road and I see them and the dust caps are just hanging there going, no, somebody should have told the technician they actually thread together. So again, cleanliness is going to be key in that. Next slide. So the initial installation, we're going to use the OTDR. We can do it as point-to-point elements. We can do it as point-to-multipoint elements. We're going to identify all of our attenuation values and so forth. To troubleshoot, we want to isolate the trouble, whether it's feeder, distribution, or drop. And from the ONT to the FDH, working backward, we're going to use the power meter and the visible laser. On the next page, we have a picture of one of the red lasers. These are Class 2 or Class 3 lasers, by the way, so which means that the Class 2 is 1 milliwatt, the Class 3 is the 5 milliwatt version. I prefer the Class 3. It's brighter, but I can look for faults a lot easier with the higher power level. Another thing is that because of the wavelength, 670 nanometers, they're operating out of band from the ONTs and OLTs, which use an indium gallium arsenide phosphide detector. And these detectors will not pick up 670 nanometer wavelengths. So don't worry about using a red laser on a live system. It will not disrupt it, okay? And again, it's visual, so we can get quick continuity. Just don't look at the red light. Put it against a piece of paper, red dust caps, yellow dust caps, whatever. But it's an excellent tool for troubleshooting, and we can identify obvious faults, pigtails, connections. Contaminated ferrules actually will glow on it. Macro bins, micro bins. We can test visually. You can hook it up on an input port of a splitter, and we'll get red light coming out of all the output ports as well for quick continuity, and it would tell. Obviously, we could see if one port was bad or damaged. And on the next slide, we're going to talk about that. So, with connectors, we're depending on quality of the cleanliness and that, which means that we can clean, but if we can't see it, it's not going to do us any good. So we need an inspection scope. The neat thing with the new digital scopes is you can store traces, you can compare. They have automatic functions to tell you if it is a fault and what type they are, and if they're in the qualified IEC standard zones. But anyway, cleaning is going to be critical for the success of the network and prevent failures. Let's go to the next slide and let's talk about reflection testing. So reflections, Fresnel reflections, those ones that cause the spikes on the OTDR, they affect the laser operation, and therefore it affects the signal quality, whether it's bit error rate, and of course if we're having a problem we have to resend signals, and latency comes into the game. And the connectors are the major causes of reflections, but it could be an open port at a patch panel just as easily, or at a splitter location. You can do it. If reflections are more critical on analog circuits versus digital circuits, and so this is why we have the angled physical contact, or APC polish, on the connectors. We assume that the installation could have an RF overlay system on it, so therefore we're putting the more reflection insensitive polish on those ferrules, which is why the reason for the APCs. UPCs are good for digital systems. But we do want to resolve the problems. There is a product called an optical terminator that is basically a dead-ended plug that where no reflection comes from the backside of the plug, and you can plug these into ports and reduce Fresnel reflections very easily, and terminators cost about $10, $15, depending where you get them from. They're not overly pricey. It just depends on how many you need. And again, pay attention to the cleaning materials that you're using, because these do affect the reflectance. And just another note, remember that optical return loss and reflectance are not the same. Optical return loss is the sum of the fiber, connector, splitter, splices, everything. It's a sum number, and system manufacturers want to know the ORL values to guarantee a bit error rate level for their equipment. But if your ORL level is out of spec, then you need to identify what is causing it to be out of spec. And that's normally an individual component, which now we would use the OTDR to measure the reflectance to find out which one's out of spec, because once we resolve it, we should have our ORL values come into the appropriate values. And on the next slide, just using the OTDR to measure reflectance, there's a couple things here at the bottom, 2 dead zone boxes or 1 dead zone box. Let's go to the next slide and let's actually show these. So, in this case, we're putting a length of fiber with connectors at each end. We're connecting from the OTDR to the patch panel, in essence. And so we're pushing the span out. So, most of the time these are 500 meters or 1,000 meter lengths of fiber in a box. But it allows us now to measure the reflectance of that front-end connector. And remember, the first connector closest to the laser is the one that has the highest reflectance and affects it the most. So it's the more critical one. The one that's 10 or 20 dB down at the subscriber, it'll be attenuated 10 or 20 dB, that reflection, to get back. However, if we put a dead zone box at the far end, we can also measure the reflectance of that far end connector as well. Now, if we go up one more slide, excuse me, I didn't put that slide in. If I would have removed it, if I didn't have a second dead zone box, I could still put a terminator in and still measure the reflectance far, and I just can't measure the attenuation. So the summary and that, one, we're really depending on the manufacturer's alarm system to identify the scope of the problem. And once we know the extent of the problem, whether it's one PON or multiple PONs or multiple fibers for other applications, that's when the OTDR really becomes useful for it. We try to eliminate the transmission equipment using an optical power meter, and that means we have to have good records, known values, and that to do so. And we eliminate it by segments. We work from the subscriber back toward the service provider, and we really need to have good value measurements. So at this point, we're moving to the question and answer period. And because I am operating remote, I'm going to have Rick ask the questions, and I will respond to those. There's also before Rick starts, there's a special that we have. We have a DVD. It's about an hour and a half and about, I don't know, a dozen chapters on it. But it breaks down troubleshooting disciplines from either a maintenance perspective or a restoration perspective, whether it's splices, connectors, splitters, fiber to the home, DWDM, all these different elements, and it's a special price. So it would be good for a lot more information that I'm able to give you in 50 minutes in a webinar here. So Rick, can we have the first question?
Yes, Larry. The first question is, how do you isolate a problem in a splitter?
Okay. Okay, so the case is there's two solutions here, and one is if it's a 1x32 splitter and we have everybody offline, then we can use the OTDR again. And again, remember, we need the higher dynamic range to be able to measure through the splitter. And in this case, we would we could increase the pulse width depending on the drop where the splitter is located. But we could use the OTDR, measure through. We need the higher dynamic range on the OTDR to do so. Or if it's only a few, say one or a few users, do a truck roll, and again measure your disconnect your output connector. If it's only one user, disconnect the output connector and just check the power level. And if you have your original measurements of it, then you can just do a quick comparison for it. If all the users on that splitter are offline, we want to disconnect the input connector. And you can keep the power meter in DBM mode power, measure the input power level, and then reconnect the connection, go to the opposite side of the splitter and test the output side. The difference between that will give you the loss for each one of those ports. And if you want to test 32 ports, you could do the same. You could also, in that case, zero the meter. When you did your initial power reading, you could just zero the meter to dB, and then when you tested the output ones, it'll tell you the loss on every one of those ports directly in dB. Otherwise, you just do a little math real quick on dBm minus dBm in that port. I hope that answered it. Next question.
Can I test at 1550 nanometers instead of 1490?
Okay. Okay. Okay, I think the question is there a difference between 1490 and 1550 nanometers? So this would take us into a few tangents here. And so if you're say your OTDR, you have a standard OTDR, 1310, 1550 nanometers. Use it at 1550. The difference in attenuation, fiber attenuation, we're talking hundredths of a dB. It's so negligible between 1490 and 1550. Just go ahead and use 1550. Now, that's one of the tangents. On the other case, power meters are normally calibrated for the different wavelengths, and you should just be able to use the power meter at 1490 or 1550 very easily. Now, as far as the network operating, if 1490, the basic band is your downstream digital content. So normally that's your internet, your data, Ethernet. If you're doing IPTV, that would be at 1490 nanometers. The 1550 nanometers is only being used for RF overlay. So for, in other words, cable TV, analog, amplitude modulation systems. Okay, so hopefully I answered that one to satisfaction. Is there another question?
Yes. Will high ORL cause low signal alarms at 1490 nanometer wavelength? If so, what practices should be exercised to determine location of the problem?
Okay, so optical return loss again is the total reflectance of the span. So the 1490 nanometers is your downstream transmission to the subscribers, and so if the ORL value is out of spec, then it definitely could affect the signal quality or bit error rate of the span. So the case is now is it one user or is it multiple users? If I would think because the 1490, see the ORL is the reflectance coming back to the OLTs transmitter, or laser, which is at 1490 nanometers. So it's affecting it. So the case is it should affect every ONT and that on it, not just an individual one, because it's affecting the laser that's talking or communicating with all the ONTs and that. So it should be a sum of all of them, not just an individual one. Okay?
Another question, Larry. Is it prudent to use 1625 or 1650 nanometers on an OTDR since both wavelengths will show macro bands or any other stress-based losses better than at 1550 nanometers and can be used on a live system without affecting operations?
Yeah, one of the reasons the ITU has specified 1625 and 1650 nanometer testing is that one, it's out of band of the operating systems, and secondly is these wavelengths into the long and ultra long bands are much more sensitive than 1550 nanometers for macro and micro bands. So yeah, if you have an OTDR with 1625 nanometers, one, congratulations that you have one. Two, if you don't have an OTDR with that wavelength, it's always good to have one, because there's cases where it will pick up faults that put it this way. I've seen in splice trays where ribbons touching each other at 1625 nanometers, you can pick it up with an OTDR. So yes, 1625, 1650, either one. They are recommended by the ITU for new systems for maintenance applications, and so it's a great function. Okay.
What is the best direction to make troubleshooting, OLT to ONT or ONT to OLT?
It depends on how many of the ONTs are in alarm or having problem. If it's all of them, then you can go from the OLT downstream. If it's only a few, you're working the opposite direction than that. Okay.
Another question, Larry. What is your recommendation for cleaning fiber connector ends and bulkheads?
100%. I always like this question because, in one case, I don't want to get specific to manufacturers, but you do need to visually be able to visually inspect for both a contamination perspective and a damage perspective, and then. What we don't want is low-grade isopropyl alcohol in particular, which actually increases reflectance. So, and you should be, when you're cleaning, you really should be cleaning both surfaces. So, the neat thing now with all the new cleaning products out is that we can put inside the adapter and clean the mated side in a patch panel or in an OLT port or ONT port where we couldn't do that decades ago. And now we have these neat, really great products to do so. But yes, my recommendation is to clean, and also to have the tools for inspection to make sure that it's cleaned properly. Okay.
Larry, what is the maximum testing distance in feet for a VFL red light?
Again, the VFL, the red lasers, they come in two different power levels. So you have the 1 milliwatt and you have the 5 milliwatt version. And so obviously if you have more power, you're going to have more range. But when you're talking, there's a couple things here, and one of it is, if we're dealing with like indoor cable jacketing, yellow for single motives, and it's cordage type thing, where you can pick up a macro or micro bend and you can actually see the light. That's great. However, in the outside plant, we're normally dealing with black polyethylene jacketed cables. We're not going to be able to see a macro or micro bend with a VFL. So we're basically using it for continuity testing for drop cables. And, normally, they're good for 1 or 2 kilometers just for but he's asking for feet, so that's about, 3,280 or 81 or double that, so we're talking 5,000, 6,000 feet, and again, personally, I like the 5 milliwatt, for troubleshooting, and that versus the 1. And if anything, get one of each and take a look and say where you're going to use it. But close in, macro and micro bins around pigtails, splitters, these type of things, they're wonderful. And if there's a fault there, you'll be able to see it visually, externally. But once it's in the black jacketed cable, you're not going to be able to.
Another question, Larry. Can I measure with an OTDR in one direction, or do I need to measure in both directions?
You could, well, it depends, again, if we're talking a feeder, our backbone, then we want to measure bidirectionally. We want to measure at 1310 and 1550 nanometers or 1625 if you're lucky enough to have it. No, but the closer we get to the end user, when we start getting into the distribution and drop, then we're pretty much you're only going to test it one direction. It's just the massive amount of testing taking place. And the most important measurements we have are the optical power levels, versus the distance. So once you first put in the span, get your distances, get your attenuation values, your reflectance values with the OTDR. And then afterward, then you want to start picking up your power levels, your OLT transmit and receive, your ONT transmit and receive levels. Plus, as noted, the power levels before and after splitters. You really want those.
Okay, Larry, a couple questions here. We are using active ePTP system. Should we be using the 1625 nanometer for testing? We do not now, my understanding, it was for PTMP systems.
Yeah. Okay. Point to multi-point.
Right.
Well, first thing, 1310, 1550. If you do a comparison and the 1550 loss is higher than 1310, then the 1625 is going to be even higher yet, still. So that, what we're really looking for is at the longer wavelengths is the attenuation higher than it is at 1310. So, but it really doesn't make a difference if it's a point to multi-point as far as the OTDR. The difference is whether you have enough dynamic range on the OTDR to measure a point-to-point multi-point system and that. Okay?
Last question, Larry. What are the most important tests to conduct at the GPON FTTx network?
Power levels. We need to have the OLT's transmit level. That's at 1490 nanometers in dBm. Test it, document it. Go to the splitter, input power level at the splitter, output power levels of the different ports. And those levels, I really like to see the power levels noted at the FDH or wherever the splitter is. And then last is the power levels at the ONT, the receive power levels. The upstream is nice to get, but I'm really depending more on the downstream. If I have to replace an ONT, put it this way, if my power level is good and I don't have an obvious problem, then it's going to be on the copper side of the ONT. So it's a case going, am I going to replace the ONT or am I going to get to the next level of troubleshooting to find out what that problem is? And again, we're assuming one unit, not a whole lot. Here, just an individual user. And every once in a while, unfortunately, it could be, I've seen it where alarms were incorrect. It was an F connector on a video feed or so, but the more critical ones is the power measurement, of course. And also, Rick, if that was the last question, if you want to go to the last slide, I believe.
Sure.
Okay, or the second to last. So it was one that has my email address on it. It says to contact me directly, please send an email, larry@lightbrigade.com. So if anybody has questions that I didn't address, I will be responding to the emails and that. And if you want to talk on the phone, better yet. But I am available. And I also gave you the different phone numbers there. And Rick will handle the improving one. And on our last slide, now we get to the last one, Rick, our next webinar will be in January. And this is a fun one, improving OTDR accuracy for emergency restoration. So again, we're going to be talking more about the OTDR functions here, and I'm excited to be presenting that one. I'm still putting some slides together, and always, if people have any concerns or thoughts that they want to share, get in touch. So thank you very much for attending, and we'll look forward to hearing from you.